In this video, I'm going to talk about word embeddings. Word embeddings is a better encoding than one-hot encoding and is often used together with neural language models. But first, let's see why we use word embeddings. Let's consider these two sentences. A cat is walking in a room, and then we want to predict the continuation for a different sentence, which is the dog was running in a. We see here these two sentences are pretty different if we just look word by word. It's just the word in and a that are common between the two sentences. However, if we know something about language, it still would make sense to predict bedroom for the second sentence, because the cat is walking in a bedroom and the dog was running in a bedroom, very similar sentences. It also turns out, if we look at these words in more detail, that they are related, even though they are different. So the first word in both sentences have a and the, which are articles. Cat and dog are both nouns that also happens to be pets. Was and is a different sentence of is. Walking and running are both verbs that communicate movement, and so on. So in this example, we would benefit from having a good encoding of words. This is why we want to use word embeddings. Word embeddings are encodings of words that show relations between words. It will help the model generalize to be able to do predictions, or we can see inferences on examples it hasn't seen in the past. In this figure, which describes the details of word embeddings, the idea here is that we will embed the word in an n-dimensional space. That is, each word is represented by an n-dimensional vector. Therefore, word embeddings are often also known as word vectors or distributed representations, because the representation of word is distributed across a number of variables. So, in the chart, the words that are related to each other are close to each other in the vector space. For example, we can see running and walking are close to each other because they are verbs. And this table shows the coordinates for different words. For example, cat has coordinates 0.9 and 0.8. If we look at this number of this sentence, the cat is walking in the and a dog was running in a, they are very similar sequences. For that perspective, if we train a neural network to output a certain output given the first sentence, it's very likely that it will output something very similar when we present the second sentence to it. Of course, in reality, word embeddings are very large and greater than 2 dimensions. Sometimes it's like 64 or 128 or even more dimensions. Let's look at how we can use embeddings in a neural network. The way we do that is we use embedding layer. This figure illustrates what an embedding layer looks like conceptually. We have a one-hot encoding input. So in this case, we assume a vocabulary of 5 distinct words. So we have a one-hot encoded vector that is 5 elements long. We want an embedding size of 3. The way we do that, we have this one-hot encoding input, and then we feed that to 3 neurons. These 3 neurons have no activation functions, so they are linear neurons. This one, denoted by the len in this figure. The embedding for a given word can be found on the connection from the word to each neuron in the embedding layer. So let's consider the first word. The output for the first neuron would be 1 times the weight WE00 and then plus 0 times the weights from the all other inputs because all the other inputs are zeros. So each neuron here will basically output the weight that connects to the neuron, to the word, to this word. In reality, we wouldn't implement an embedding layer like this. Instead, we would implement it with a lookup table. But drawing this embedding layer, this gives you an idea of how we could actually build it as neurons. And then we would be able to train these weights using backpropagation. So we'll not have to select the embeddings for each word. Instead, we will have the model learn these embeddings when we are training the model to solve a problem. Let's now put word embeddings together with language models to arrive at language models that no longer use one-hot encodings, but that use word embeddings as inputs. We do this by adding an embedding layer in the beginning of the model. In this case, the middle model where we have multiple embeddings, we would typically tie these weights together so that although we have multiple instances of layer, they would all share weights. Here is an example where we have trained a language model that uses embeddings on a text. We have then looked at the resulting embeddings. So we took the embedding for a specific word shown in the leftmost column here, and then we were looking for what are the embeddings that are closest in vector space to that word. For example, if we take C and looked for the other words that were close to it in the vector space, it turns out that the model had chosen to put the word visit, adorns, and induce, and we see that they are all verbs. Similarly, if we looked at the embedding for the word of and looked for embeddings that are close to this word, and we found that with, in, and by are in the vector space. And all of these are prepositions. So we can see that this language model has learned something about the language structure, even though we didn't specifically tell the model that there were prepositions or verbs. It just found this out by how the sentences were built that it was training on. And I will show you in the next video how we can do that by using TensorFlow.